In the case of factorial, though, we could actually just implement it as a loop instead of implementing it as a recursive function. So you might notice that factorial can actually be implemented with for loops. So to really see the value of recursion, let's look at an example that's a little bit more difficult to implement without it. So this is Fibonacci sequence, or at least the first few numbers of Fibonacci sequence. Fibonacci sequence is a list of numbers such that every number in the list is the sum of the previous two numbers. So 1 plus 1 is 2, so the third number is 2. 1 plus 2 is 3, so the fourth number is 3. 2 plus 3 is 5, so the fifth number is 5, and so on. 34 plus 55 is 89, so the 11th number is 89. The reason this is a good candidate for recursion is to calculate the 11th number, we need to know the 10th and the 9th number. But to calculate the 10th number, we needed to know the 9th and the 8th number, and so on. To find a given number, we need to know the previous two numbers, but to find those numbers, we need to know their previous two numbers, and it'll always require us to go all the way back to the beginning. So what would that algorithm look like? It's actually pretty similar to our factorial function. We're asking for the Fibonacci number located in location n, or located at index n, and as long as we're looking for a number beyond the second number, because the first two numbers are 1, then we'll return the Fibonacci number for the previous element in the sequence, plus the Fibonacci number from two earlier spots in the sequence. Once again, these minus signs mean we're going to continue working towards our base case. Eventually, we will return 1. So if, for example, we wanted the fifth number, well, 5 is greater than 2, so it will return Fibonacci 4 plus Fibonacci 3. Fibonacci 4 is also greater than 2, so it will return Fibonacci 3 plus Fibonacci 2. Fibonacci 3 is once again greater than 2, so it'll return Fibonacci 2 plus Fibonacci 1. Neither 2 nor 1 are greater than 2, so it'll finally return 1. But what's important to note is that Fibonacci sequence as implemented here is very inefficient. And the reason for that is we're going to have a lot of duplicate function calls. In our previous example, if our original number was 5, then the first time it runs Fibonacci, it's going to try to run fib 4 plus fib 3. But fib 4 is going to require fib 3 plus fib 2. And fib 3 is going to require fib 2 plus fib 1. But over on the left, fib 3 is again going to require fib 2 plus fib 1. All the fib 2s and fib 1s will return 1, but all the others are always going to spawn 2 additional calls to Fibonacci. So if we were looking for the 11th number, for example, then it'll call fib 10 and fib 9, but fib 10 will also call 9 and 8. And that 9 will call 8 and 7, while that 8 calls 7 and 6. And that 8 will call 7 and 6, while this 7 calls 6 and 5, and that 7 calls 6 and 5, and that 6 calls 5 and 4, and I'm running out of space, and you can tell that this is going to get very big. In fact, it explodes exponentially. So this implementation of Fibonacci is very inefficient. We could make it more efficient if we replace these calls to Fibonacci directly with a function that looks up and sees, have I already calculated the Fibonacci number at location 5, for example? And if so, just go ahead and grab that value instead of recalculating it manually. We would probably do that with the dictionary, where the keys in the dictionary are locations in the sequence, and the values are the Fibonacci numbers at those locations. That way we can very quickly see, do I already know the value that corresponds to the key 5? If so, go ahead and grab it. If not, go ahead and calculate it. But most importantly, it's going to remove all those duplicate calls to Fibonacci with the same value that we've used before.